Good morning, everybody. My name is Gabriel.
I'm Christopher Wantham.
I'm Aaron Otis.
And I'm Scott Rizzo.
And the name of our project is Designing Mathematical Models and Feedback Control. Our mentor is Deepti Kanapon, and a principal investigator at Design Bombay. Now, before we begin this presentation, we're going to have a little bit of a demonstration. Scott.
No pressure.
Okay. Now, you can see that Scott has developed an algorithm inside of his brain that allows him to self-correct. Now, this self-correcting behavior, thank you, Scott, for that demonstration, is what we basically encapsulates what we are studying in this project. So essentially, what we're trying to model is a scaled-down version of what's called a gantry crane. Now, if you look, there's a large load attached to this, and you want to kind of minimize the oscillations going back and forth because it becomes a real safety issue. That basically is a control system, and control systems are basically everywhere, from the temperature in this room, which is regulated by a control system, to autopilot settings on an airplane. And so we started out this project with three main goals. The first was developing a mathematical model to input into MATLAB, which is a computer program that would help us minimize these oscillations going back and forth, to develop better methods of error analysis, and also basically just refining the overall process. Next slide. Okay. Now, if you look to the left, if you look closely to the left, this is the very undesirable behavior that we're trying to minimize. And to the right is essentially what we've done to try to minimize that. And we're basically still refining that process. And so to give you an idea of some of the equipment that was involved, I'm going to pass it over to Scott.
Okay, so this is a closer look at some of the equipment that we're using. This is the body or the cart of our gantry crane model. And here we have three cables. We have one that's a power cable that just powers the motor, and then two data cables that are directly related to the sensors that we use. One sensor that detects the position of the cart as it moves along the track, and the other to detect the angle of the pendulum as it's swaying back and forth. And this is the rod that we're using with the load at the bottom to simulate the pendulum itself. And when you put it all together, you get our scaled down model of our gantry crane. So now this is the scientific steps that were taken to basically get the gantry crane from doing practically nothing to getting it to do exactly what we want it to do, or as close as possible. And the first step that was taken was to design a mathematical model using Newton's laws and other methods. Then we linearized that mathematical model to get an approximation of the model itself. Then we go on further to optimize using a numerical method called the linear quadratic regulator, which gives us the formula for the motor self-correction, kind of like how I was doing. And then we implement that and experiment, we get our data. But even then, we're still not satisfied. We still feel with that data we can get better performance. So we take a parameter we feel that would improve that performance, we adjust it, put it back into the optimizer, get a new formula for the motor self-correction, then I'll implement that and experiment, get more data. Now this cycle continues through every parameter that we feel is important to get the optimal performance of our gantry crane. And now Chris is going to talk about the linearized model itself.
Okay. Well, our mentors actually started it off. What they did is they got a free body diagram of our miniature gantry crane. And taking into consideration every force, they use differential equations and dynamics to get their mathematical model. Now, from there, they simplified it, and out of that, they put it into a linearized model and simplified it. And the output of that was this red oscillation you see here, as it has a sampling effect. Now, this resembles a lot the movement of the crane as it moves along. I'll play the animation for you guys. See how it moves from side to side, and it just kind of dies down? This resembles it a lot. It's actually somewhat of a graph or similar to the displacement as time goes on. And from there, we simplified the model into what we call the decay movement. Now, as assembly function is just much easier to put into MATLAB or programming in order to simulate it and solve it. As you can see, they both approach zero, and what this means is that our system here is one that becomes more stable. And it means that our system will almost come to a stop every time. This is a real world, so we don't have a complete for sure stop.
Okay, and this graph represents some data we collected. Basically what it is the position of the load on the crane, which is the blue line, in relation to the path that we desired it to go, which is the green line. As you can see, there's kind of a lot of oscillations, which means it's swaying back and forth a lot. And the way we measured it was measured our performance was by measuring the peak overshoot, which is the very first peak there, the very top of that peak in relation to the point straight down below it. And what an overshoot is, real quick, is just how far the load passes past the desired path that we went.
All right. So in our trials, we decided to tinker around with something called voltage weight. Now that is one of the parameters in the mathematical models input into our programming. Now the voltage weight is a system that we use to regulate how much voltage was input into our link card here. It made sure that there wasn't a power overload to keep our equipment safe and so that we may keep on testing. Now through different trials, we found that even though it's a close race, the 0.4 value for the coefficient was the best outcome we had with a less than 3.5% error margin. It's pretty good, but we're going to keep on that.
And so this graph represents that using that optimal voltage weight, we were able to reduce the peak overshoot, and also it had a much better dampening effect.
It's much more stable. All right, now this here is when we decided to mess around with a different parameter called the angle weight. Now it's very much similar to the voltage weight, but this one regulates the angle. It puts it into the mathematical model and takes into consideration how much of an angle we don't want it to go. And as you can see, well, the first result there actually, the highest one is that 0.4%, that lowest one from our previous point. And so as we messed around with as we tested around with a higher angle weight, we saw that we would get lower percentages until the last one we tested there, in which it was less than a 1% error margin. That's pretty good if you ask me.
And this graph represents that our best trial. As you can see, the peak overshoot is very small, and it is very close to where we wanted it to go.
Much more stable.
Okay, in conclusion, we found that the voltage weight, which we thought was much more important, the most important parameter, was not as important as we initially thought. We also thought that by lowering the voltage weight, we would get more error, but we actually saw that it reduced the error. We found that the angle weight tended to have a much higher amount of influence on the performance. And while we didn't get to fully test to find the optimal angle weight, it appears the trend is as we keep increasing it, the performance becomes much better. There are also several other parameters. As I said, we didn't get to finish testing the angle weight. There are several other parameters we didn't get to test, and that's going to be tested in further research by our mentor, Jonathan.
And we would just like to thank our PI Bassam, the directors Maria and Jens, our presentation advisor Stephanie for all the help that she did, our mentors Jonathan and Deepti, our RA Jordan, and our roommates Daniel and Armando for helping us put this whole thing together. We'd also like to thank the Jack Kent Cooke Foundation for giving us the opportunity so that we can learn more and grow personally. And I'd like to thank UCSB for hosting this, and the ECE, which is the Engineering and Computer Engineering Department.
And thank you all.